Okay, what's poppin', everybody? It's time for some statics final exam review. Here I've got a question that's, it's not quite a pulley, but it still uses the same technique as a frictionless, or as a friction-full pulley. And so we can go ahead, or I think it's belt friction is probably the correct term. So I'm gonna write belt friction just so we have that up here. Anyway, we're going to talk about a belt friction problem, so we'll dive right in. It says a rope is attached to the top corner of a 450 Newton block, passes over a fixed drum, which is what this is, and is attached to block B as shown. The coefficient of friction between the 450 Newton block and the floor, right here, is 0.3. The coefficient of friction between the rope and the drum is 0.6. Okay. A lot of information there. So we'll start with part A. It says, part A, assuming the base dimension of the 450 Newton block, is large enough to prevent it from tipping, so essentially no tipping, determine the smallest mass of block B that will cause the 450 Newton block to slip with respect to the floor. So essentially we're asking to check the conditions of what will cause this to slip. And normally in a case like this with a block like this, we're talking about friction at the bottom, we'd have to look if it would slip or if it would tip because the force is on top. In this case here, we only have to worry about it slipping because it tells us that it won't tip. Because they don't give us a bottom dimension here at D, but they just say D because they're assuming that it won't slip. So part A, we'll jump into part A. Assuming the base. So this is where free body diagrams are always necessary. I'm going to say necessary. If you do a problem like this and don't draw a free body diagram, you definitely won't get full credit because these are probably a good 5 points here. So we'll go ahead and draw. That's supposed to be kind of the centroid of it, which is another topic you'll need to know for this exam. Yeah, I'll put this dimension up here. Not sure if dimensions are going to be terribly important for what we're doing here, but always put them in. And this is 20 degrees above, and then I'm just going to label this one T for tension. Okay, and then on the ground here, we can go ahead and just draw on the middle the normal force, just normal for N. And then lastly, this is where we have to draw in our friction just on the ground here. So the friction on the ground, it's always going to try to counteract the direction of traveling or the direction of motion. So if we take a look with the force from the rope here pulling on it from weight B, it is going to want to travel to the right. And because it wants to travel to the right, the friction will be going to the left. And it's always a good idea to try to predict friction in the right way. I feel like I haven't really done this because most of the time I'm able to predict if friction's correctly. But if you, for whatever reason, draw it in the wrong direction, you might luck out and end up getting, if you're solving for friction directly, you might get, let's say, a negative value, which means it's in the opposite direction, which is theoretically the correct direction. But that's only just a check your work thing. It probably won't work in this instance here, so I probably shouldn't mention it. But anywho, we'll keep going with this. And so we can go ahead and using all of our information here, I think that's everything we need for a free body diagram. We can go ahead and solve some of the forces in the y. Is equal to N minus 450 equal to 0. So N, the normal force, is equal to 450 newtons. That's some information we'll need. And then we could say at slip, F equals F max. And what we need to know about F max is that is equal to N times mu, the normal force times the coefficient of friction, which in this case is going to be 450 times 0.3 as they gave us earlier. And if I get my calculator out, just a warning here, I do not have the answer key for this problem. I'm just doing it how I would do it if I were taking the exam myself. We got 135 for that one. 135 newtons. So I very well could be going down the wrong path. But hopefully by now, you guys trust me well enough to be doing this right. Hopefully I know it well enough for myself. If I don't, I'd be kind of disappointed. But yeah, I don't have the answer key, so hopefully this is correct, and hopefully I'm leading you guys in the right direction at least, even if it isn't correct. But anyway, our friction max is 135 newtons. And so we can go ahead and we're assuming that this is going to be slipping, so this is going to be 135. So we'll go ahead and take the sum of the forces in the x. Sum of the forces in the x, we're going to have our tension force. Oh, you know what? I made a mistake talking about not having an answer key. I did make a mistake because in the sum of the forces in the y, we also have the tension force acting upward. So that's going to throw a little bit of a wrench into things. But, you know, when you make a mistake and you catch yourself, hopefully you'll have enough time to go back and fix it. And if not, just make do, fake it till you make it, I guess, if you make the mistakes. Because mistakes are an ever-present part of life, and definitely an ever-present part of statics. So all that beautiful work I did is gone. It's null, it's invalid, incorrect. So normal force is going up, and tension force, so plus, and this would be, tension force is going at a 20-degree angle, so T times, that'd be the sine of 20 degrees. Minus 450 is equal to 0. Ready? SOHCAHTOA, opposite, so height there. And so, this gets kind of tricky, but we can say n is equal to 450 minus t sine 20 degrees. So, ultimately, maybe I haven't explained this yet, but in this problem, since we're trying to solve for what block B is, I think the first thing that we need to solve for is what the tension in this rope is here, and then using that tension we can calculate what it will be over this friction pulley here. You could probably use the equation first and find what the equation would be, but ultimately it's not going to be helpful because this weight of B is going to be a variable anyway. So I think solving for T in its own is easier, makes more sense than starting with that equation there. I mean, you could do it and then you just have to backtrack a little bit, but I think this is a more linear way of doing it. And so with this information, I'm going to go ahead. Sum of the forces in the x is going to be equal to, and this time it's going to be t times the cosine of 20 degrees, cosine along the horizontal there, minus f is equal to 0. And then let's see what we know here. It gets a little bit challenging here, but I think we can still say at slip F equals F max, which is going to be equal to the normal force times, and this time it is equal to mu, but I'm just going to go ahead and say 0.3. And so we can go ahead and take this equation down here. We could say F is going to be equal to this just by algebra, so in turn we're going to say N is going to be equal to T times the cosine of 20 degrees, and then I'm dividing both sides by the 0.3. Okay, hopefully that makes sense there. And then I am going to go ahead and substitute this in to this equation up here. So T times the cosine of 20 degrees divided by 0.3 is going to be equal to, we're substituting for N, so it's going to be equal to 450 minus T times the sine of 20 degrees. Alright, so now we probably want to get the T's on the same side. So we're going to have T times the cosine of 20 degrees plus T times the sine of 20 degrees is equal to, is going to be 450 times 0.3. And then just to write this out differently, we could say T times cosine 20 degrees plus sine 20 degrees, because that's just factoring out the T, is equal to, and I think we calculated that before in my calculator, 450 times 0.3 is 135. 135. And then we're going to go ahead, my calculator again, we're going to have T is going to be equal to 135 divided by, and in the denominator it's going to be cosine of 20 degrees plus sine of 20 degrees. And that should give us 105.5. 0.3. I'm just going to write out the whole thing. We'll round at the end. There's a lot more digits there, but you don't have to get carried away with it. But as long as you give yourself a lot of significant figures, then at the end you round, then it'd be more accurate than if you started rounding now too early. But anyway, that's going to be in newtons. So that's the tension in this rope here, along here. Now we need to solve for what the tension is here at B, because let's see what we've got here. I'm just going to check over this work real quick. And hopefully, if you guys see something wrong with it, you know, you can always email me or leave a comment down below or whatnot. Tell me if you agree or disagree. I've definitely run into my fair share of mistakes in Platoon and in these videos, I'm sure. And so, I mean, you saw me have to redo a mistake that I made there. And so F is equal to, I like to be slow and steady, and that definitely helps. In the exams, you need to pick up the pace a little bit. I'm assuming it's 4 problems. Now I can't remember if it's 4 or 5 problems, but probably 4 problems for 2 hours is what we're looking at. And so, and that was putting that in for that, and then dividing by. Okay, I think 105.328 is probably correct. Just want to make sure I'm not going too fast and making stupid mistakes. Anyway, we'll keep going with this. And so I'm going to go ahead and draw a free body diagram of B right here. Because what we're solving for is the mass. We're solving for the mass of block B, and they say MB. But we can't really know the mass without knowing the weight in this case. And so here, I'm going to draw weight, which is equal to mass times gravity. And then up at the top here is going to be T2, tension 2. Okay? And this is where we have to start looking at this friction, this drum here. They call it a fixed drum. I guess that's what you could call it. It's probably the correct term. This drum here, we need to take a look at. And so this might be where things get a little bit more confusing, a little newer stuff of what we've been talking about. Excuse me. Here we have the drum. Just drew it as a circle here. We've got a force going that way and a force going that way, which it was 20 degrees above the horizontal here, which means that up here it's 20 degrees below the horizontal, going the opposite direction. And we could say mu is equal to 0.6. Now this is where it gets important with labeling, because this has friction in it, one of these tensions is going to be bigger than the other. And that's why you have to think about where things are moving. And so ultimately we care about which one is going to be bigger than the other because we have an equation. And the equation is T2 is equal to T1 times E times mu beta. And let's circle that equation. And this equation is essentially, if we know the smaller tension force, T1, we multiply it by this, we can solve for the bigger tension force, T2. But we need to know which of these two tension forces is bigger. And that's where we need to take a look at the whole system and think, which direction is this moving? And ultimately, if you take a look at this, we want this to be sliding this way. We want this to be sliding, and therefore the tension would be pulling it here, and the rope would be going down along the drum like that. And if the rope is going down along the drum like that, then we should be able to see that the tension force here should be bigger than this tension force here, because it'd be overtaking it essentially, if that makes sense. Because if this tension force were bigger than this one, you'd be going this way. It's almost like if you're playing tug of war, essentially. And as soon as the rope starts moving, you know, the one that starts moving is going to be the side that has more pull on it. And that's going to be this one. So T2 and T1. Well, we've already solved for T1, and that's this 105.328 newtons, and that's T1 right there. And now we need to get this other information. And so mu, they gave to us as 0.6, and we wrote it over there. Beta is kind of tricky to solve for in this case. We need to take a look at exactly what's happening in this drum here. And so beta is going to be the angle that the belt comes into contact with the drum. and it always needs to be in radians. You can't use degrees in here. You have to use radians. But it might be helpful to look at it first in degrees and then convert to radians. And that's essentially saying 360 degrees is equal to 2 pi radians. Rads. Pretty rad, bro. Oh, God. Sorry. 360 degrees is equal to 2 pi rad. And so we need to be able to figure out where exactly this is coming into contact here. I'm going to draw the circle of this. And this is where maybe if you draw lines to where the rope ends or where it leaves contact. So here at the side it leaves contact right on the edge of the circle here, which should make sense. It's just tangent to that and you can see how it's drawn there. Over here it's kind of tangent at the top left of it. And this is where geometry and a knowledge of geometry comes in handy. And I wasn't particularly good at geometry, but hopefully we can figure this out. And I'm going to go ahead and draw a dotted line to the top there. And so this is one thing where I like to visualize it in a different way that I'm not sure is how they taught you properly. But essentially, take a look at this line here and this angle here. Because we know this angle in the middle is 90 degrees. That's a right angle from the top of this to the right of here. We made it that. Now we don't know what this angle here is from the top of this to where the rope leaves contact. However, we do know this angle of where the rope is going down. And so the way that I like to imagine it is, what would it look like if we took this tension force and somehow twisted it upward? We twisted it upward so that this angle here is 0 degrees and that it's going out straight. Well, if we were to twist, and then its base would be leaving at the top here. Well, if we were to twist this up 20 degrees, we'd end up twisting this 20 degrees to match it. And so using that, we know that this inside here is 20 degrees. It's just having to visualize exactly how it's happening. And so, because once you twist this 20 degrees and it goes even, then we know that if the rope is even along that way, then it would be touching the top here. And this would be, this angle here would be 0. And so now this is angling down, that's got to be 20 degrees. They both turn 20 degrees. So our total angle beta is equal to, that's 90 plus 20 is 110 degrees. But we need to convert it into radians. So we have 110 degrees times 2 pi radians. Handwriting's a little bad there. 360 degrees. And so we can cross out the degrees. We'll get it in radians. Get the calculator out. 110 times 2 pi over 360. We get 1.91986. And again, 1.91986. I'm just going to write it down, the whole thing, just so we have enough sig figs that our final rounding should be as accurate as possible. You don't have to overdo it, but it definitely helps to have some extra ones. And so now we can write out our equation. T2 is equal to T1 times E to the, whatever mu is 0.6, and whatever beta is, we already solved for it, equals beta is 1.1986. I'm actually going to go ahead and substitute in. We know what T1 is. And that is this 105.328. Hopefully in your exams you have nicer handwriting than that. For the sake of what we're doing here, it's fine. In my eyes, it's fine. So we've got 105 times, ooh, that's a lot of stuff there. We've got E to the 0.6 times, I'm going to go ahead and drag that down and put it in there. And we've got 333.3 newtons. Okay? And therefore, using this free body diagram here, we know that that's equal to the weight of block B, which I'll label WB. And so, therefore, as we have here, WB is equal to MBG, or 333.3 newtons divided by 9.8 is gravity, is equal to the mass of block B, I'm just going to copy over that whole thing again. 9.81 is, we could say 34.0 should be kilograms is what we've got. So 34.0 kilograms in our answer box up there. That's how you solve for part A. There's a lot of work, but a lot of that was kind of just me reasoning through things and making mistakes. We're still not done though, because that's for part B. It says, for the value of the mass determined in part A, determine the minimum value for D that will prevent the 450 Newton block from tipping. So we'll go ahead down here, and this is where, whoops, drew a line through that. So our part B does depend on part A. This is something where if you're in the exam and you couldn't solve for part A and you have maybe 20 minutes left, 15 minutes, and you know you can't solve for part A, you're just stumped on that, go ahead and just pick an arbitrary value for your weight. We don't have to because we know what our weight and our tensions are. Our tension we got is 105.328 newtons. So I'm going to go ahead and redraw the free body diagram. You could tailor the one that we have up here, but I drew it in a way that wouldn't really be conducive to that. So we've got our free body diagram up here. That's a really high angle, but it's still at 20 degrees. It's 105.328 newtons. We've still got friction down here. And now this is where we need to reason with, what would it look like? We've got the dimension here, D at the bottom. What would it look like if it were tipping? And another thing I forgot. The weight is 450 newtons, and it's going to be right in the middle of D, so D over 2. What would it look like if it were on the verge of tipping? Well, if it were on the verge of tipping, then our normal force would be on this right edge here. And that's where you kind of have to, again, visualizing makes everything a little easier in statics. It's not one of those where you can just memorize how things work. You have to kind of look at it. And just think in your head, what would it look like if this were to happen? But I mean, as we would be pulling on this edge here to the right, this thing would end up, or this block would end up kind of going and tipping over in that direction. Very faint lines here. And if it were to tip, all of the normal force would be in this corner here. And we do need the dimension over here, 1.0 meters. Okay. And now we need to take some of the moments about a point. And this is where we have to determine which point would be the easiest. And so we have a few options here. We could solve for, or we could sum a moment about this point here where the normal force and the F are. And then that would allow us to solve for what D over 2 is, because we have to have the distance D over 2 for this force, and this force would be D. And I think that might be the most logical way. You could also solve it about here, and then you would have the tension and the weight would not be causing a moment, but the tension would be causing a moment, and the friction would be canceled out. But then you have the normal force here. We don't know what the normal force is. We could probably calculate it out, but that's an extra step we don't need to do. So if we take the moment about here, which I'll label as point O, then we don't need the normal force, and friction is canceled out, and we have these two weights. All we'll have is, for unknown, is D. We'll have D over 2 and D. So we'll go ahead and do that. So some of the moments about O, and that's why you have to be strategic. You have to think ahead. Kind of like playing chess or something. You have to think ahead and say, what would happen if I were to do this step? Of course, you don't need to think ahead 12 steps. You can just think ahead 1 or 2. And so summing the moments about O, one moment that we have is 450, and it's going positive, right-hand rule. Hopefully you guys know that by now. 450 times D over 2 minus, and this is where we have to split off our tension into two different forces because it's at an angle. If it were directly horizontal or directly vertical, we'd only have one, but we need it in the X and the Y. So we'll go ahead and start with the vertical component. So 105.328 times the cosine of 20 degrees. Then we want the distance, and the distance is going to end up just being the 1 meter because it's pushing off at this side, so the moment about O is going to be this 1 meter times the horizontal. And then next is also going to be negative 105.328. This is going to be the sine 20 degrees times, and this time the distance is going to be d. And all of that is going to equal to 0. And there's a lot of ugly math that we could do here to figure it out. And we will do it to find what d is. So we'll go ahead and calculate all of this out and do algebra. If you do have a calculator like mine, you could learn how to do a solve function and just plug the whole thing in and get what d is. But I'm just going to run through the whole thing here. Feel free to skip ahead a little bit, maybe 5, 10, 20 seconds. 225d minus, we got 105.328 times trigonometry cosine of 20 times 1, so we don't really need that, minus 98.976 minus 105.328 sine of 20. That's times d, so we don't need to put that into the calculator. 36.024, let's say that, d is equal to 0. And then we have to do some more algebra. We'll take 225 minus that, minus, we got 188.976, d is equal to, and then we'll just add this to the other side, 98.976. Therefore, d is going to be equal to, I'm just going to get up in my calculator. It's the 98.976 divided by 188.976. And we get d is 0.524 meters. Oop, just playing around with my calculator. So d is 0.524 meters. That is the smallest that d can be to prevent it from tipping. If d were any smaller, then the moment caused by this tension force here would be enough to counteract the moment caused by the weight here. And so that's our second answer here. So we go ahead and plug that into our answer box up above. And that's everything you need to know for this problem. Hopefully that helps you guys review some things. It helps us review friction just on the surface, and then it helps us review belt friction on the block here and kind of how to get the angles. That's really what tripped me up. To be honest, looking at it the first time was kind of daunting at first, and then you just have to visualize it again and make it easier for you to figure out how things are acting. If you were in the exam and you could not figure out the angle, if you're getting stuck, you know, it wouldn't hurt if you just said 90 degrees or pi over 4 would be what that is. Just anything to make it easier on yourself. Or again, like I was saying, if you couldn't solve for the tension in the first part, go ahead and pick an arbitrary number. You could have picked 100 or something. And then at least therefore you have the work. So please, good luck on studying. Please study and work through these problems and run through them. But yeah, don't let yourself get stuck. And if you do get stuck, find a way to advance yourself on the stuff that you know. So at least you have the work down. Because blank pages, they might be really easy to grade, but they're not fun to grade because you always feel bad. There's so much potential that could have been there, at least a few points, you know? So at least try for that. But thank you guys anyway for watching this video, and hopefully it made sense. I apologize for the mistake I made in the first place, but everybody makes them, so don't feel bad if you make mistakes. You know, it just happens in this class. It's a hard class, so hopefully you feel comfortable in it by now for this exam. Past the final, you know, the statics is a huge part of every class you'll take. Past this. Friction I haven't really dealt with too much, maybe a little bit in dynamics, but definitely some other parts, especially with anything, especially in civil engineering. If you take structures, it's basically just statics review, and same with mechanics and even fluids. So anyway, thank you for watching, and good luck studying on this.